Kailash, let me see. Did everyone's here? Okay, good. Everyone's here. Okay. Can see the slide? Anyone?
Yes.
Can. Okay, guys. So, yeah, halfway of nuclear physics. So, what you learned in the beginning of the topic so far? So, let me. So, we're done with the mass defect. We're done with the binding energy. Okay. We talk about E equals mc squared. What is meant by mass defect? What is meant by 1U? Then we went to talk about binding energy. Okay. So the nucleus which has the greatest binding energy per nucleon categorized as the most stable element. Yes. So yeah, we learned about nuclear fusion and nuclear fission. Okay. Okay. Now we're going to talk about. You should recall back in nuclear process. I think 4 quantities are conserved. Okay. What are the things conserved in the nuclear process? Charge is conserved. Okay. Total nuclear number is conserved. Okay. Mass energy is conserved. Okay. Mass energy. Don't just say mass is conserved. Don't say energy is conserved. You must say mass energy together conserved. Only in nuclear reaction. Okay. Remember, recall back the conservation. And another one thing you can nuclear number, charge, mass energy conserved. Another one is missing. Anybody? There is another one conservation is missing. Anyone? Anyone can tell what is another conservation happens in nuclear reaction? Conservation of?
Momentum.
Oh, very good. Momentum. Conservation of linear momentum. Momentum is conserved. So actually 4 things conserved. If you go in universities later, let's say you major in physics, if you do nuclear physics back, you see not only these 4, there are many conserved, around 7, I think. 7 quantities is conserved. For timing, the other 3 quantities is not revealed. Okay. Remember these 4 concepts. Okay, so today's lesson, we're going to continue about radioactive decay. Okay, so what our discussion today is going to be about half-life. Okay, about half-life. Last time you just know half-life, but you don't have any formula. But now we're going to introduce a formula really linked to half-life. Okay, last time question just asked, after 1 half-life, what is the mass left? So you know it's half. After 2 half-life, what is the mass left? So you say quarter. But now they might ask, how much the mass left after half-life? Okay, the intermediate timing. So how to find? So we need a formula. So that's what we're going to learn here today. Okay, first introduction, recall back what is meant by radioactive decay. So please remember this. What is radioactive decay? A type of spontaneous random disintegration experienced by heavy unstable nucleus become more stable product with lower total mass by emitting radiation such as alpha, beta, and gamma. Okay, so you learn what is spontaneous, what is random in your AS already. What is meant by spontaneous? Why radioactive is spontaneous? Because unaffected by external factors such as pressure and temperature. Why it's random? Because we don't know how many nucleus and which nucleus will disintegrate at a particular time. It's totally unpredictable. That's why it's random. Okay, so radioactive decay. So how do you measure activity of a substance? So recall back, very useful for your design experiment. If your design experiment comes out about something to do with radiation, then you have to tell what device to be used to measure the radioactivity. So the device to be used is, of course, GM tube. Not enough you tell GM tube, you must take GM tube connected to a rate meter. Okay, useful for your design experiment. Okay, so measuring radioactivity by using a GM tube and rate meter. The rate meter tells you the count rate, how many counts happens in a second. The alpha particle, when the radiation get into this GM tube, what type of gas content inside the GM tube? Argon, right? It contains argon. Argon is an inert gas, but this radiation can make the argon to lose the electron, and the argon which is become positively charged and the electron which is negatively charged will accelerate it towards the two different terminal. Okay, the center rod I think is positively charged, negatively charged. The body is positively charged. The argon and the electron will accelerate towards the different terminal. They're going to count how many argons has been released. It counted like a count rate. If the count rate high, we say lots of argon atom has become ionized. So that means the radiation level is high. Okay. Okay. So this is GMT with the rate meter. Okay. So one correction here, or not say one correction. You need to be alert here. When you use GM tube, without source also you get reading. That reading called as what? Background reading, background count rate, or background reading. What is the source of background reading? You should know. What causes background reading? Due to cosmic ray, due to the radiation comes from low intensity radiation from small quantity radioisotopes found in the ground. Okay, radon gas from the ground, cosmic rays, and the stones surrounding you also, some are radioactive, small radioisotopes there, so releases radiation. So you should know what is the source of background radiation. Cosmic ray, radon gas from the ground, and stones surrounding. Okay, and of course from medical hospital. Okay, X-rays. Okay, now we go to the calculation part. Okay, so first, if you have hold on, I used to tell this. If you have like 1 gram of uranium, and let's say you have 2 kilograms of uranium, you place a GM tube for both substance, GM tube. Okay, the reading going to be same or different? The count rate. Both are uranium. One is 1 gram, another one is 2 kilograms. The reading detected by GM tube same or different? Anyone? It's going to be same or different? The GM tube reading. Same substance, but the mass is different. The one with a greater mass will have a greater activity. It will have a greater activity. So greater reading because got more mass. So that means the activity proportional to what? The count rate reading, which is the activity, is proportional to what? It's proportional to the number of particle, radioactive particle available. So that's what the first line said. DNDT is actually activity. DNDT is actually activity. The activity is directly proportional to the number of radioactive particle available. If the number of particle more, the activity is going to be greater. Okay. So the activity is equals to negative lambda n. Negative lambda. Why negative? Because the lambda called decay constant. It's decay. Decay means reducing. Reducing. So they put negative. But I tell you, in your Cambridge, they ignore the negative. They just use activity equals to lambda n. So in your exam, ignore the negative. You need to put negative. So A equals to lambda n. So A is what? A is activity. Okay. Like count rate is activity. N is number of particle. Lambda, very important quantity. We label it as decay constant. We call it what? Decay constant. Okay, what is decay constant? Is a fraction of the total number of atoms that decays per unit time. Okay, I have another better definition, which is, I think, more easier to remember. Okay, please write down. It's in the Word file. What is meant by decay constant? Okay. Yeah. So you can see here, decay constant. What is decay constant? Decay constant, the probability that an individual nucleus will decay per unit time. Please remember this for decay constant. Okay. It's a probability. One mark, probability for an individual nucleus to decay per unit time. It's called decay constant. It's actually a probability. Okay. So let's say decay constant is 0.7, 0.5. Lambda is 0.5 per second. What is the meaning of that? That substance may be uranium. That means every nucleus in the uranium has chance to decay about 0.5 times. That means 50% of chance to decay in every second. That's called decay constant. Again, what is that? The probability that individual nucleus to decay per unit time. So now tell me, you have two substances, A and B. Lambda A greater than lambda B. Okay, which substance more unstable? A or B? Lambda A is greater than lambda B. Which substance more unstable? Should be A. Greater the lambda decay constant, greater the decay constant, more unstable the element. Okay, because the probability to decay by any time is very high. It means it's going to disintegrate very fast. So put in your mind, when the lambda is high, the element is the stability become poorer, bad. So its half-life also going to get short. Okay, when lambda is big, this element is very unstable. That means the half-life going to be very short. Okay, very short. Okay, so please take down decay constant. Okay, so first equation has been introduced. What is the first equation? Activity equals to lambda n. This lambda has lots of unit, but the unit normally can be per second, can be per day, can be per month, can be per year. Got many units. But when you use this formula, A equals to lambda n, the lambda must be per second. Remember, very important. When you use A equals lambda n, lambda must be per second. Don't use per year, per minute. If in the question, if they give per year, you have to convert to per second. Okay, let's say you have 0.0001 per year, the decay constant. Per second, how much? Per second going to be how much? This is the probability to decay in a year, you know. The probability to decay in a second going to be smaller or bigger? Smaller. So you divide your times. So you divide by 365 days times 24 times, 60 times 60. Change to seconds. You get lambda in a second. So when you use A equals lambda n, make sure lambda is in a per second. So lambda is per second, n is number of particle, activity unit got special name called becquerel. Call it becquerel. The activity unit is becquerel. Okay, let me just temporarily go to show what is meant by becquerel. Yeah, 1 becquerel. Okay, the unit is becquerel. Unit for activity. Okay, becquerel. 1 becquerel means we said 1 disintegration per second. It means one atom transformed in a second. Okay. Okay. So that's the first question, equation. Any questions? No questions, Okay, let's continue. Okay. Now, actually, we have three formulas under radioactivity. This is the first formula, activity lambda n. Okay. Okay, let me ask you one question. In exam, if they ask a question like this, to say there is a carbon, there is a uranium, which is as a one which has a 500,000 atom as an activity of 50 becquerel. You have another uranium now, which is only 1 million. Okay, atom. What is the activity for this? So A equals to lambda n. You can use two data. The first data you can use to find the lambda. So A you put 50, lambda n you put the number of atom. So work out the lambda. Whatever answer you got is in per second. Now use the second data. A you are looking for lambda, the one you got it earlier, and put 1 million. So you get the new activity. Okay. So you know number of atom, you can find activity. But if you know, you need to know the decay constant. Okay. So this is the first equation. Okay, now this is not the famous one. Under radioactivity, as I told you, you have three equations. This is not a famous equation. Okay, sometimes you will be using A equals lambda n, sometimes. But the most famous one is the next one. This is the famous equation in radioactivity, very commonly used many times. This equation. This is the second equation. N equals to N naught E negative lambda T. Okay. Okay. N stands for the number of particles still remain. Remember, the N is number of particles still remain, haven't disintegrated yet. N naught is the original particle. Okay. N naught is the original particle. Okay. So N naught is original particle.
Undecayed.
Yeah.
N is undecayed.
Yeah, undecayed. So undecayed particle. Haven't decayed yet. Yeah, correct. True. N naught is the original particle. The original when the time is 0. Lambda is decay constant. T is time. Maybe time after 5 hours later. You put T as 5 hours. You'll find the number of particle which is undecayed after a certain time. Okay. So what is the use of this formula? To find how many atoms, how many particles still undecayed after a time t. Okay, the derivation is this. You don't need to know derivation, but actually this formula obtained from the first formula. Activity equals to negative lambda n. Actually, I said in reality you need to put negative, but Cambridge they ignore the negative. But for the derivation, you have to use the negative negative lambda n. So you see dn n, they rearrange it, they put n one side, the dt the other side. So this is the integration actually. Integration of n naught with the limit. The initial value is n naught, final value is n, time taken 0, final time is t, negative lambda t. Okay. Here should be still dt, not yet integrated. Now after that, when you integrate, 1 over n is become ln n. I believe under maths you learn, right? Integrate 1 over n, what do you get? Ln n, right? Ln n and naught negative lambda dt, you integrate, you get negative lambda t, right? Integration. So include the limit n naught, n naught here become ln n over n naught. Here t minus 0, you put negative lambda t. So yeah, you rearrange, you get this formula. N equals to n naught e negative lambda t. Okay, most dominant equation. Here, this n naught, general formula is x equals to x naught e negative lambda t. Okay, this n can represent different type of physical quantity. This n can replace with a, can be activity. That means the formula can written as what? A equals to a naught e negative lambda t. It can be in terms of activity. That means after time t, what is the new activity? It also reduces exponentially, like number of particles. N, just now I show you n. Count rate. Count rate also can represent the same pattern. C equals to C naught E negative lambda T. What is the count rate after time T? We can use this formula. Okay. Finally, what is the mass undecayed particle? The mass after time T. You can write the formula M equals to M naught E negative lambda T. So four quantities can represent the same pattern of equation. When number of particle decays, activity also drops, count rate also drops, the mass also drops. All drops exponentially. Okay. So don't think this pattern is only belongs to number of particles. It belongs to mass, count rate, activity. Okay. Okay. Now the lambda t, right? There is a trap here. The lambda here, if lambda given per year, okay, the probability is 0.2 per year. They give in terms of year. Then the time here, the time you put in terms of years. You put in terms of years. Both must be same unit. Then it's fine. So in this equation, the lambda, not necessary you must put per second. Here lambda you can put any unit you like. But as long as time also the same unit as lambda. If lambda is per year, time is year. If lambda is per minute, time must be per minute. Got the idea? The second equation, lambda t both must have a like identical units. Lambda per year means time is year. But the early equation, this equation, lambda must be per second. It's a trap. I tell you, be careful. First equation, lambda must be per second. Second equation, lambda can be any unit. If you're confused, better change all to SI. You won't get wrong. But if the time they give year and the lambda also per year, why you want to convert? You convert more work lah. But if you confuse, better convert. Any questions? Okay. So now, so I told you what is meant by activity. Activity unit is Becquerel. How many disintegration happens in a second is activity. This is you learned this before. The graph shows that the time 0 n naught, after half-life, of course it dropped to half n naught. Another half-life it dropped to quarter n naught, and so on. So the common formula, the n after time t, okay, maybe n after certain half-life, number of half-life, you can say half power of n, half power of n times the n naught, right? N naught. Then n after multiple of half-life. Let's say the half-life is 3 half-life. So we can use this formula. Half power of n times n naught. If it's 3 half-life, so it's going to be half times power of 3 n naught. So the one still remain is n naught over 8 after 3 half-life. Okay. Or you can use the earlier formula. N equals to n naught e negative lambda t. Okay. Put the lambda, put the time, you can get the n naught. N. You get n naught over 8. Okay, but from O levels, I think how many particles left? They normally go for multiple of half-life. But now as I said, they can ask what is the particle left at any time. So which formula to be rely on? This formula rely on. This formula is versatile. Can get the remaining particle at any time you want. Just put the t in. You can get that. Okay. Okay, so that's the second question. Okay. Okay, next. Last equation to be introduced. Equation for half-life. You should know what is meant by half-life. A famous one. The half-life of radioactive nuclide in the time taken for the number of radioactive nuclide to disintegrate to half of its initial value. So half-life is time taken for the activity to drop to half of its original value. That's half-life. Okay. Bigger the half-life, smaller the half-life, the element is less stable. Okay. The one very less stable will have a very short half-life. Okay. How half-life linked to decay constant? That's what we're going to do. Okay. The third formula you have to remember is this one. This is your half-life formula. T half-life is, or you can use this formula. This is better. T half-life is equals to ln 2 over lambda. This is the last and the third and the last formula in radioactivity. How they got this equation? The derivation you must know. You must know the derivation. The earlier equation derived, you don't know, it's fine. But derivation for half-life is in your syllabus. So you must know how to derive it. Okay, look at the derivation. The derivation of half-life formula is obtained from the second formula. N equals to n naught e negative lambda t. When the time is half-life, t half, the number of undecayed element, the n will be n naught over 2. Right? When the time is half-life, the n will be n naught over 2. So we put n naught over 2 here, t is half-life. So mathematical arrangement, n naught cancel. So here you become e lambda t, negative, you get negative. But when you bring the other side, here supposed to be r, become 2. Okay. So E2, we bring ln both sides. So ln 2, here E disappears, lambda t power of half comes down. Then you get half-life formula, ln 2 over lambda. This could be a guys, can you hear me?
Yes.
Can okay. What is the consequence of the third formula? So it tells you that how decay constant related to, so greater the okay, in this formula, the lambda can be any unit also. You can put lambda in any unit like, okay. Lambda you put per year, the half-life time you will get answer in years. Okay. Okay, so that's it. So what is the three formulas you know? A equals to lambda n. N equals to n naught E negative lambda T. Half-life equals to ln 2 over lambda. Here lambda must be per second. These two equations, lambda can be any unit, but unit for lambda and time must be same. Remember. Okay. Another one trap. This n here is the particle which is decayed or undecayed. This one undecayed. The one still haven't decayed. Okay. Another one conclusion. Half-life inversely proportional to the decay constant. Greater the decay constant, smaller the half-life, the element is less stable. The unit for activity is what? Backcurrent. The SI unit for activity. Okay. Okay. So three equations. The derivation of these two equations you don't need to know, but the derivation of the half-life equations you have to know. Okay. How do you derive? Start from the second equation and you replace with n naught over 2. T is right, T off, you get the answer. Okay. Okay, now let's do some examples how this three equation is used. Any questions, guys, from here before we do the questions? No questions, Okay, so let's try some questions. Okay. Yeah, the n equals to n naught E negative lambda T. You bring ln both sides, you can plot a graph ln n versus T by using y equals to mx plus c. It's going to be a straight line where the gradient is negative lambda. Okay. So many materials have a different types of half-life. Uranium has 4,500 million years and radon just 1 minute. We are lucky to have radon as a very short half-life because radon is found from our underground, from the earth soil, from the core of the earth, like got a lot of radon gas produced. So that's why those who are staying for a long time underground building, like car parks, car parks which build underground, the lowest ground, maybe the third basement basement 3, you go and park. If you stay there for a long time, let's say some security guard stays there for a long time, at the third floor, they have to be careful with their radiation level, because underground might have a lot of radon gas available, so can cause a very high radioactivity. But as I said, good news is radon gas half-life is short. Okay. One example. Come on. Use the three formulas. Figure out how are you going to do these questions. Two minutes for you. The half-life of radium is given. What fraction of radium would remain after 1,000 years? 1 times 10 power 3. So what formula you think suitable? What question wants? What fraction of radium would remain? I mean, the question asking for what? Asking for n over n naught.
Yes.
What? Right? This is the fraction of the radium remain. What? the number of particle over the original particle. So the question asking for N or N naught. So which formula is the best? The second one, right? N equals to N naught E negative lambda T. You can find the fraction. Just bring the N naught to the other side. So identify the formula. Which formula? The second formula. Do you know lambda T? Do you know yes, you know. Yes, you know. But do you know lambda? Yeah, lambda we can find. How do you can find? Half-life equals to the third formula. Half-life is equals to what? Ln 2 over lambda. So you see, if you know half-life, you can find lambda. If you know lambda, you can find half-life. Like frequency and period, lambda and half-life. So half-life is given, so you can work out the lambda. But half-life is in years. Do you want to convert to per second? Do you want to convert to second? I think not necessary. Yeah. So if half-life is years, lambda you get in years. So put a lambda in years, time also in years. So no need to convert. So that's the solution, right? So first, the working found the half-life. So can find the lambda, you know. Yeah, find the lambda first. Here they found lambda T together. Okay. Then N equals to N naught E negative lambda T, you can find the fraction. Okay. Any questions? Hope you understand the working. Okay, so the equation to be used is second equation. The question looking for fraction of the atom. Okay, go to the next one. Okay, 1 minute for you. Read the question, identify which equation to be used. Identify which equation to be used. Is it the first one? A equals to lambda n equals to n naught E negative lambda T, or half-life equals to ln 2 over lambda. Or you need to use more than one. Check. The radioactive cesium as a half-life. So half-life given 30 years. So we can find lambda. If the initial number of cesium is this much, or this your N naught, what is the number of cesium nucleus that decay? This also you have to be careful. Asking what is the one already decayed after 90 years. The one already decayed. But the formula, if you use the second formula, N equals to N naught E negative lambda T, the N is what? Decayed or undecayed? The N is undecayed. Remember, the N is undecayed. So I think you can use this formula. You can use this formula, find the N, but the N you obtain is undecayed. Then how do you want to find the decayed? Just minus with N naught minus with this N, you get the one already decayed. So I think the formula you are supposed to use here is the second formula. Right? This is the working. Look at the working. Hope the idea in your mind is you have two methods actually. I don't encourage you to go for the first method. Because 90 days is 90 years is 3 half-life. One half-life is 30 years. So 3 half-life. So 1 over 2 power of 3 times the original. You get the one decayed. The one remaining. Okay, then 10,000 minus the remaining, you get the one decayed. I suggest you go for the second equation, which is quite versatile. N equals to N naught E negative lambda to be used. Okay, but we need to find lambda first. Half-life given, find the lambda. Here they put lambda t last year. We multiply by the lambda t. Put the lambda t, find N over N naught how much. So 0.125 fraction still remain. So the one decayed is 1 minus 0.125 times 10,000. You get the one already decayed. Okay. So which method I prefer, I want you to adapt is the method 2 because very versatile. Anytime you can find. The first method only works for multiple of half-life. Might looks easy, but I think better go for the second one because it's versatile. Anytime you can find the decayed or undecayed particle. Any questions? Okay, so let's proceed. Another one. Oh no, this one no need now. We come back. This all come back. Let's go to the other questions. From other papers. Pass here. Okay. So actually we're done with the topic already. Okay, we're done with the topic. We're done with the half-life and decay constant. So now we can go ahead with the past years lah. But I want you to add more on this topic. Is please recall back for nuclear physics. Please recall back your mole concept. You know, mole. How do you convert mole to mass? How do you convert mole to number of particles? These two you have to know. Volume, not necessarily. Volume also sometimes. This concept you have to recall back. This you learn under chemistry, right? Last time. Mole to mass, you multiply what? Multiply by the relative atomic mass. RAM is it? RMM. What do you call? Relative molecular mass. So mole change to mass. You have to know that. Mole change to number of particle. What do you do? 1 mole. 1 mole, how many particle it contain? Multiply by the Avogadro constant, right? Na. Correct? Na, how much is the value? Na 6.02 times 10 to the power of 23. Recall back. Mole to number of particle. Multiply by Na. Mole to volume. Multiply by how much? 22.4 dm cube. This value they will give in exam. 1 mole of substance in standard temperature pressure. How much is the volume? They will tell you. So you have to know this conversion. Okay, because in exam they will tell you like activity is 0.2. There is 1 mole of uranium. How much is the activity of that substance? 1 mole. So the formula comes to mind is A equals to lambda n. But they give mole, but you need to know particle. So you should know how to convert mole to particle. Okay, multiply by Avogadro constant. Okay. Any questions? So please include this on top of that knowledge, on top of what we learned just now. This part you need to recall. They expect you to know. They won't teach you here, but they expect you to know. Very important. You're going to use it under radioactivity. Okay. Okay, now let's do one question. Okay, this is Juno 2. Okay, let's give a try. The first question. Define the term radioactive decay constant. So what is lambda? Lambda is the probability for a nucleus to decay per unit time. That's lambda. Okay. Next, state the relation between activity, sample of radioactive negative. Cambridge, they ignore the negative. So lambda is decay. Okay, guys. Okay, now I give you 1 minute. Please calculate for me. Part C. Read first. Get me the answer. Okay, how do you do this? Radon is radiative gas with half-life of 56 seconds. For health reasons, the maximum permissible level of radon in the air building set to 1 radon atom for every this much of molecule of air. 1 mole of air in the building is contained 0.024 meter cube. Calculate for this building the number of molecule of air in 1 meter cube. So 1 meter cube got how many molecules? So this is ratio, right? 0.024 meter cube got 1 mole of air. That means got 6.02 times 10 to the power of 23 molecules. Okay. So 1 meter cube got how much? So of course 1 divided by 0.024 times 6.02 times 10 to the power of 23. Get the number of air particle. Correct? Ratio, right? Any questions? Part 1, A1, C1? Good idea. It's just ratio. Okay, next. What is the maximum permissible number of radon atom in 1 meter cube of air? How many radon particle can be permitted in 1 meter cube of air? So how to find? They said 1.5 times 10 to the power 23 molecule can have 1 radon. So what do you do? Again, this also ratio, right? 1.5 times 10 to the power 21 particle can have 1 radon. Now this much of molecule, X particle, how many radon? That's a question, right? So how do you get this value? So X divided by 1.5 times 10 to the power 21 times 1, you get the number of radon available. X is the answer you got. Okay, get the number of. So this is totally chemistry, you know. Just using a mole concept, identifying how many particles are available. That's why I say the mole concept we have to remember. Mole to N, mole to mass. Better recall back. Okay. So last question. The maximum permissible activity of radon per cubic meter of air. What is the maximum activity of radon? The maximum permissible number of radon we get here. The question asking for what is the activity for that number of particle of radon? What formula do you use? One activity. Anybody? The first, second, third equation. Which equation to be used? You want activity. You want A. So what do you know above? Above you know N. So use A equals to lambda N to be used now to find the activity. N, you got the number of radon gas above here. This is your N. Okay. How do you find lambda? Lambda, do half-life given? Check. Half-life is given. It's 56 seconds. So good. So you can work out the lambda. How you can work out the lambda? Lambda equals to ln 2 over half-life. Yeah, correct. So ln 2 over 56 and put the whatever n you got from above. So you get activity in Becquerel. Okay. And be careful when you use this formula. Don't forget lambda must be per second. It's a trap. Okay. When you do more questions, you will know that it's going to be a trap. Must be in per second. The purposely will give you other unit to make sure you change to per second. Okay, class. So that's all about this topic. Okay. So as a homework, maybe on Friday, we can discuss these questions for 1 hour. Tomorrow is your practical. Okay. So Thursday, Friday, we discuss this paper, the remaining one. Just give a try these questions. Okay. And check the answers. Any part you don't understand, we can discuss on Friday. Any questions? Any questions, guys? No questions, huh? Okay, so see you on Friday, huh? See you on Friday. We will be discussing the nuclear questions, nuclear question passes. Okay, so I stop here.